told him to bring an extra pair just in case.
Okay.
So. But it's live streaming, so.
Oh, okay.
So basically, you're saying when they give you a function like set up x equals the square root of 2y or something, and then the y integrated. Yeah, because you can use both formulas. When you're revolving
Even though his class is like, even though his class is impossible to fail. Impossible? I want to finish with a good grade at least.
Yeah.
Oh, he put the grades in? Yeah. Yeah, he only. I was happy. I was like, you're 50-60.
Giovanni, are you with me?
No.
I thought you were a team for a class.
I'm the SI leader.
Oh, just an SI leader?
Yep, just an SI leader. Hello. Yeah. He said he would have a question on oscillations, but I have a couple examples, so it's all derivations. Yeah, I guess he didn't post the actual example problems.
Yeah. Okay.
True. Yeah. Yeah.
He from Cuba.
Oh, I gotta, for this one, let's say, you know how the car has like Because I seen another example, they use the four wheels, and this one uses include the.
Oh yeah, because the force is there's only two wheels of variance in the car.
Once we do it,
Okay.
I know you have to start.
Yeah.
Andrew said, he said this year we just gotta turn the pace and go through all of it and now give it a break right there.
Yes, and now
Every single class. You just wanna like flip through it, give you a break. Flip through it, give you a break. We got a fully break after the day.
Hello? Can everyone hear me? Maybe? No? Hello? Can everyone hear me? Alright guys, we're gonna get started here quickly, so if you guys could settle down. Alright, so this is the physics review for Del Barco's 2048. We're gonna be focusing on rotational kinematics, torque, kinetic or rotational energy, and angular momentum, and also oscillations. Just want to make sure. Can everyone hear me fine or not really? Okay, let's put this closer. How about now? Maybe? Yes? No? A little bit better? Alright, I'll try my best. Alright, so this is a review that I made. If you go to the website, ucfstudyunion.wordpress.com, you can find it there and follow along. If not, you can just follow through here. Just want to have a disclaimer that some of these solutions may be wrong, though I don't think they are. So we're going to get started, and the first few problems are going to be rotational kinematics, all right? So I'll read the problem. A large wheel of cheese, initially at rest, accelerates at a rate of 10 radians per second squared. The radius of the cheese wheel is 2 meters, and it has 3 parts. Find the time it takes to complete 10 revolutions. Find the angular velocity at the moment the cheese wheel hits 10 revolutions, and then find the distance the cheese wheel has traveled across the ground in 10 revolutions. All right, so I just want to remind you that for rotational kinematics, it's very similar to regular kinematics. The only difference is that you change all the linear variables with angular ones. So we're going to change displacement with angular displacement. We're going to change velocity with angular velocity. And we're going to change acceleration with angular acceleration. All right, so we use the same equations. So this is what the problem looks like. We got a cheese wheel. It starts at rest and it starts rotating with a constant angular acceleration of 10 radians per second squared. We're given the radius. The first question asks to find the time it takes to complete 10 revolutions. So we're going to look at our kinematics equations. We're going to use the displacement equation. So we have delta theta is equal to omega I t plus 1/2 alpha t squared. Okay. The wheel initially starts at rest, so we can take out that first term since there's no angular velocity initially. And then we have an equation that has delta theta, which is the angular displacement. We have alpha, which is angular acceleration, and then we have t, which is the time. All right, so the first thing we need to do is find the angular displacement that we're searching for. So the question says to complete 10 revolutions. So we need to find the delta theta that corresponds to 10 revolutions. So the way you do that is 1 revolution is 2 pi radians. And if you want 10 revolutions, you just multiply the 10 by the 2 pi. So our delta theta is going to be 2 pi times 10. All right, we plug that into our equation. We're given everything we need to know, and we can solve for time. All right, so when we solve for time, we get 3.545 seconds. So that's the time it takes for the cheese wheel to rotate 10 revolutions. Are there any questions on how to do this part? All right. So the second question asks to find the final angular velocity at the moment the cheese wheel reaches 10 revolutions. So again, we're going to look at our kinematics equations, and the one that's going to help us out the most is this one. We have omega f equals omega initial plus alpha t. We just found the time it takes to do 10 revolutions. We were given alpha, and so we can simply solve for omega f. So then we plug in our values, 10 radians per second squared times the time we just found, and then we get our final angular velocity, which is 35.45 radians per second. All right. Now for the third part, we have to find the distance the cheese wheel has traveled in making the 10 revolutions. So this one isn't a kinematics equation, but it is the equation to relate angular quantities with linear quantities. So we're trying to find a linear quantity, which is the distance across the ground, but we're given an angular quantity, which is our angular displacement. So we have this relation that delta x is equal to r delta theta. We were given r. We know delta theta is the 2 times pi times 10. So we can plug that in, and then we get 125.664 meters that the cheese wheel travels across the ground. So are there any questions on this problem?
Where does the 2 pi 10 come from?
2 pi 10? All right, so the question asks to do 10 revolutions. All right? 1 revolution is equal to 360 degrees in a circle, right? And 360 degrees in radians is 2 pi. So 1 cycle is 2 pi. And I want to do 10 cycles, so I have to multiply 2 pi by 10. All right. Any other questions on this problem? Right, so if you do use the linear kinematics equations, so the delta x equals vit plus 1/2 at squared, and then change a to angular acceleration by doing a equals r alpha, you get delta x equals 1/2 r alpha t squared, and you should come to the same conclusion. But you can try it out yourself to see. All right. All right, we'll move on to the next question. It's another rotational kinematics problem. So we have Bob is driving his super awesome car. He starts in reverse and ends driving forward. The angular velocity of the tires when he is reversing is 20 radians per second, and the angular velocity when he is driving forward is 30 radians per second. He performs this with a constant angular acceleration. It takes Bob 5 seconds to make this change in velocity. The radius of the wheels are 0.5 meters. Radius of the wheels, okay. 3 parts to this question. Find the angular acceleration of the wheels, find the initial linear velocity of the car, and find the final linear velocity of the car. All right, so again, this is rotational kinematics, so we're going to use our kinematics formulas. This is what the problem looks like. So we have the car, and initially it's in reverse, so the wheels are rotating counterclockwise. And then when we end, we're going to be ending in driving forward, so our angular velocity is going to be clockwise. All right, we're given all our values. So the first part is asking for the angular acceleration. So first things first, let's choose a positive direction. So I'm choosing clockwise as the positive direction, but you can choose either way. It won't make a difference So we're going to use omega f equals omega I plus alpha t. And then when we plug in our numbers, we have to be very careful with our signs because we have to associate it with how we chose the positive direction. So omega final is clockwise, so it's in the positive direction. So I'm going to put a positive value for omega f. Now omega I is in the opposite direction, so I need to put in a negative angular velocity there. So we just plug in our values, then we solve for alpha. We get alpha equals 10 radians per second squared. All right. So the second part is to find the linear velocity. So similar to the last question, we just need to relate angular with linear. So to do that, you just multiply the angular quantity with the radius that we're working with. So we're going to multiply the initial angular velocity with the radius of the wheel. Then when we do that, we get a negative 10 meters per second. And notice that the sign is still there, which indicates that the linear velocity is also in the negative direction, which would be to the left. All right? And then we use the same exact formula for the third part. We just replace omega I with omega f to get Vf. And then we end up with 15 meters per second, positive, so it's moving to the right. So are there any questions on this problem? All right. Yeah, so for the biggest mistake for kinematics is usually the sign. So just want you to make sure when you do a problem like this to make sure you put the correct sign when you're plugging in your values. All right, so no questions. I'll move on to the next one. This problem has to do with rotational energy and also a moment of inertia. All right, so Bob, Tim, and Mike are standing on a merry-go-round that is rotating at an angular velocity of 15 radians per second. Bob has a mass of 100 kilograms and stands at the edge of the merry-go-round. Tim has a mass of 180 kilograms and stands halfway from the center of the merry-go-round to the edge. Mike has a mass of 120 kilograms and stands a distance 2/3 the radius from the center. The radius is 2 meters. Which kid has the most kinetic energy? And for the sake of this problem, we're going to treat each kid as a point mass. So the moment of inertia for a point mass is mr squared. All right. So again, we're going to look at what the picture or what the problem looks like. So we have a merry-go-round and we have 3 children standing on it. Those are all our values given. And we have to find which one has the most kinetic energy. So to start with, we need to know how to calculate kinetic energy when dealing with rotations. So kinetic energy due to rotation is calculated as 1/2 the moment of inertia times omega squared. All right, so if we're going to calculate the first child, we're going to use his moment of inertia and his omega. However, for all 3 of the children, omega is going to be the same value because they're all rotating at the same rate. The only thing that's going to be different is the I value. All right, so if we look at the first person, we replace I with mr squared. And then from there, we just plug in all our values that we're given. So we're given 100 kilograms, 2 meters, and 15 radians per second. We throw that in our calculator, and we get 45,000 joules. All right. Are there any questions? Move down a little bit. All right. Any questions on how to find the kinetic energy? All right. And then similarly, we're going to do the same thing, but with the other 2 kids. And the only thing that's going to change is the mass and the radius that they're standing at from the center. So go to the second kid, we plug in his mass, which is 180. We plug in his radius, which is 1/2 of the full radius. So we have 1 meter there. Then when we calculate that, it comes out to be 20.25 thousand joules. All right. So yeah, this is a lot of energy. They're spinning pretty fast. All right, and now we do the third child. We just plug in his mass and his radius. Pretty simple. And we get 24,000 joules. All right. So it's clear that the first person had the most energy, which should make a little bit of sense because he's all the way on the edge of the merry-go-round, so he's spinning a lot faster than the other two. All right. Are there any other questions on this problem? Or any questions on kinetic energy at all for rotation? All right. Then we'll move on to our next one, which also has to do with energy, with rotation. So a fan with 6 blades, each of length 1.5 meters and mass of 5 kilograms, has 500 joules of rotational kinetic energy. Calculate the angular velocity of the fan. Each fan blade is treated as a rod, so the moment of inertia for the blade is 1/3 mr squared. All right. So this is what we're looking at: a fan that has 6 blades, identical. I is calculated as 1/3 ml squared. We're given L, we're given M, and we need to find the angular velocity. All right. So we're going to use the same equation, which is K equals 1/2 I omega squared. And now we're given K, and we need to calculate I, and then find omega. So if we look at I is the summation of all the moments of inertia for each of the blades. So all you have to do is find the moment of inertia for one blade and multiply by 6 because there's 6 blades. All right? So that becomes our I value. And then from there, it's plug and chug. And you get omega equals 6.667 radians per second. All right. Are there any questions on this? All right. So we're going to get into some more fun stuff because we're moving into torque. All right. So a mass pulley system is drawn below. So actually, it's not right here. M1 is 80 kilograms, M2 is 100 kilograms. The mass of the pulley is 50 kilograms. The radius of the pulley is 0.2 meters. The height of M2 above the ground is 5 meters. The moment of a disk is 1/2 mr squared. And the question asks to find the linear acceleration of the system and the time it takes for M2 to hit the floor. So I'll show you what this problem looks like. So this is what we're dealing with. Just a pulley with 2 masses, and the pulley has a mass of its own as well and a radius. So that's going to come into play with torque. So for torque problems, it's going to be heavily related to Newton's second law, specifically if you're dealing with acceleration. So in this problem, we're finding acceleration, so we know we're going to use Newton's second law. And he has 2, because one is for linear motion and one is for rotational motion. So if we look at the left side right here, this is Newton's second law for linear motion. Net force is equal to ma. And we have 2 masses, so we're going to do Newton's second law for both of these masses. So the first thing we need to do is define a positive direction. So just looking at it, it seems pretty obvious that mass 2 is going to fall. So the system is going to rotate like this, in this clockwise direction. So I'm going to go ahead and choose that as the positive direction, but note that you can choose the other way as the positive. You can still get the same answer. So clockwise is positive. So anything that's in that direction is going to be positive. So if we look at mass 1, we have T1 going up and M1G going down. So for M1, the positive direction is upward because that's where the mass is going to head. So anything up is going to be positive. So T1 is positive, and then we have M1G is negative because it's pointed down. And then when we set it equal to mass times acceleration, We just got to make sure that the mass we use is the mass that we're doing our free body diagram on. All right. Now we can do the same thing with mass 2. It's going to be a little different because now for mass 2, down is the positive direction and up is the negative direction. So M2G is down, so that's going to be positive. And then tension 2 is up, so that's going to be negative. And then again, we make sure that we use the same mass for mass times acceleration that we did the free body diagram for. All right, so that's Newton's second law for linear motion. Now to deal with the pulley, we need to do his second law for rotational motion, which is the net torque is equal to the moment of inertia times the angular acceleration. All right, so with this, we need to draw somewhat of a free body diagram of the pulley. So the pulley looks like this, and we have two forces acting on it, T1 and T2, both downward, but on opposite ends of the pulley, both at a distance r because the radius of the pulley is r. So now we need to calculate the net torque. So the way you do this is any force that's going to cause the pulley to rotate in the positive direction is going to contribute a positive torque. And any force that's going to rotate in the other way is going to give it a negative torque. So if we look at just T2, so just looking at T2, if I were to pull from this side of the pulley, it's going to cause the pulley to rotate clockwise, right? So that's the positive direction. So the torque associated with T2 is going to be positive. So that's what we have here, T2 times R, because if you remember, torque is calculated as RF sine theta. And for these cases, R is perpendicular to F. All right, so when you do sine theta, you're going to get 1. All right. Now, if we look at tension 1, if we were to pull from this end of the pulley, it would cause the pulley to rotate in a counterclockwise direction, which is the negative direction. All right, so that's why we get a negative torque, calculated as T1 times R. All right, so then we set that equal to our I alpha, and I was given as 1/2 mr squared, where this m is the mass of the pulley, and this r is the radius of the pulley. And then alpha, which we don't know. So now we have 3 equations and 4 unknowns, so we can't solve it yet. So we need this relationship between the linear and the angular acceleration. So now that we have this 4th equation, we can solve for any of those 4 unknowns, which are T1, T2, alpha, and A. But the one we care about is A, so we're going to go ahead and substitute the alpha with the A over R. So then we get this equation. We get that R's, some of the R's cancel out here. And then when we replace the alpha with A over R, all of the R's cancel. So we're left with T2 minus T1 is equal to 1/2 MA. All right. And now what we need to do is we solve these 2 equations that we started with, the free body diagrams. We solve them for T1 and T2, and then we throw those expressions into this equation. And when we do that, we'll end up with an equation that only has A as a variable, and then we can solve from there. So we have all the masses, and G is a constant, 9.81 meters per second squared. So when we plug in all those numbers, we end with an acceleration of 0.957 meters per second squared. All right, and this is the linear acceleration of the system. All right. Are there any questions about this part of the problem?
So, like, what you did, you found the diagram, like, for the tension, the force diagram,
Mm-hmm.
and then you combine them to find acceleration? Like, I'm just, where did you pull which T?
Okay, so this one is from the free body diagram of the first mass, right? And this one is for the second mass. And then this equation is just the torque equation for the pulley. So we're working with 3 equations really. All right, and then from these 2 equations, I'm going to solve for T1 in this one and T2 in this one. And that's where I get these 2, right? All right, and then this one has T1 and T2 and acceleration. So I'm just going to throw these. So I'm going to throw this in for T1, all right, and then this in for T2. and then solve for A. All right. And then the second part of this problem asks to find how long it will take for mass 2 to reach the floor. So this is just basic kinematics. So we're going to use the position equation. So we have YF equals Y initial plus V initial t plus 1/2 AT squared. So we just found A, and T is what we're looking for. Initially, the mass is at rest, so we can cross this term out. The final height is going to be at the floor, so we're going to call that 0. And its initial height is going to be h, which was also given to us. Now, the equation simplifies to h plus 1/2 AT squared equals 0. And note right here that when we plug in A, I'm plugging in negative value here. And that just has to do with the way you do the kinematics problem. So when I did the kinematics problem, I defined up as the positive direction and down as the negative direction. So our acceleration is pointed downwards. So I need to put that as a negative value when I do this equation. All right? If you don't put it as a negative value, you'll quickly see that you did something wrong, because when you try to calculate t, you'll get an error in your calculator because you can't do the square root of a negative number. All right? So make sure you get your signs, and then you get 3.232 seconds for it to fall. Are there any questions? So this is Y initial, right? So I made Y initial height. V initial turned to 0. All right? Any questions on this problem? Any questions related? Yes, because strings can't push, so it wouldn't make sense to have those forces being applied upward on the pulley, because that'd be like saying that the string is pushing up on the pulley, which doesn't make sense. Strings can only pull. So we actually incorporated the acceleration from the pulley and the linear. So this is the linear acceleration. Over here we have the angular acceleration. But what you notice that you can relate the angular acceleration with the linear acceleration. And so everything is like the same acceleration that you're dealing with. Well, you would need to use, you wouldn't be able to find the acceleration if you didn't have these two equations. So you need to do the force diagrams for all the masses, as well as the torque diagram for the pulley. All right? Any other questions? All right. So we'll move on to the next question. So this is another torque question that involves an incline and friction. So a mass is on an inclined plane and attached to a pulley. A second mass is suspended over the pulley but is attached to a smaller pulley. These two pulleys rotate together. The coefficient of kinetic friction is 0.3, m1 is 100 kilograms. The mass of the large pulley is 20 kilograms. The mass of the smaller pulley is 15 kilograms. The radius of the larger pulley is 0.5 meters. The radius of the smaller pulley is half of that. And the angle of incline is 30 degrees. We're also given the linear acceleration, which is 2 meters per second squared up the incline. And the question asks to find the mass of mass 2. All right, so it doesn't make sense until you actually see the problem. So this is what we're looking at. We have M2 over here, and it's connected to a smaller pulley, right? And then we have M1 on the incline that has friction. It's connected to a larger pulley, but these pulleys both rotate together, so they're like glued together. We're given M1, we're given the mass of the pulleys, we're given the angle of incline, and we're given the radius of the pulleys, as well as the angular acceleration, or the linear acceleration of the system. And our goal is to find M2. So again, when it comes to problems that do with acceleration, we need to focus with Newton's second laws. So his second law for force and second law for torque. So we're going to start with force. So if we're analyzing mass 1, which is on the incline, we have the net force is equal to ma. And I'm going to look at the components that are parallel to the incline. So if you notice, we have 3 forces that are parallel to the incline. We have the frictional force, which is pointed downwards. We have tension 1 that's pointed upwards. And then we have this component of gravity that's also acting downwards. All right? So again, we need to choose the positive direction. We're given that the acceleration of the system is in this direction, so I might as well just make anything in that direction positive. So up the incline is going to be the positive direction. So T1 is positive, and we're going to subtract the frictional force, and we're also going to subtract the component of the gravitational force that's acting downward, which is calculated as m1g sine theta. All right? So we set that equal to ma. Again, note that we have to put mass 1 because that's the mass we're dealing with. And then similar, we have to solve for T1. So I'm going to solve for T1 here, and this is the expression we get for T1. All right. So now we go to mass 2, which is a lot simpler because it's just the string and gravity. So then we look at the vertical components because that's the only motion we have is in the vertical direction. And again, the positive direction for mass 2 is going to be downwards because it's the same as the acceleration. So anything pointed down is positive. So we have m2g as positive, and we're subtracting tension 2. And then we're going to set that equal to m2a. All right, and then I'm going to solve for T2 here. So I get that. All right. So the newer part of this problem is the torque. So we have net torque is equal to I alpha. We're going to draw the pulley because it makes it easier to see what you're doing. All right, so we know there's going to be 2 torques acting on this pulley because there are 2 forces. If we look at T1 by itself, if I pull from this side in this direction, it's going to cause the pulley to rotate in a counterclockwise direction, right? So that's the negative direction, okay? So that's why I get negative T1R. Again, you just calculate torque by doing R times F times sine theta. With the pulley, the theta is still 90 degrees. So when you do sine of 90, you get 1. So you can just deal with T times R. All right. Now if we look at the second tension, if I were to pull from this end of the pulley downwards, it's going to cause the pulley to rotate in the positive direction. All right, so that's why we get a positive torque. So we have T2 times the radius, which is 1/2 of R, because the smaller radius was half of the larger radius. All right, and now for the moments of inertia, we need to add them together, because you have to have the acceleration, you need the torque that will rotate both of these pulleys, not just one of them. So we have I1 and I2. So I said I1 is going to be the moment of inertia of the big pulley, and I2 is the moment of inertia of the smaller pulley. So then we just plug in our values because we know the disk moment of inertia is 1/2 mr squared. So we substitute that in. Also, we want to replace angular acceleration with linear acceleration because that's what we're given. So we replace alpha with a over r. And then when we do that, all of the r's cancel out on both sides, and we're left with this equation. All right. And you notice we don't know T1, we don't know T2, but we know A. So we're going to use the equations that we came up with before from the F equals ma. So this one and this one for T1 and T2. And we're going to plug that into this equation right here. So that's where I get this is T1, and then this is half of T2. All right? And then it's still equal to this. And then from here, the only unknown is M2, and everything else is plugging in values. So you can solve for M2, plug in all those numbers, and then the final answer is going to be 248.174 kilograms. So are there any questions on how to do anything related to Newton's second laws? Second law? Yeah, sure. Anything? Nothing. We didn't go over parallel axis theorem in Del-Barkos, so I'm not. For Del-Barkos class? Oh. So I'm not going to go over parallel axis theorem. I'm sorry. All right. So no questions on torque? All right. So the next few problems are going to deal with torque, but not using Newton's second laws. So this is more like the definition of torque. So this problem we have, Bob just bought the most ratchet shoes ever. These shoes use a bolt instead of a shoestring to tighten. Bob wants to take his shoes off. He has a ratchet of length 0.3 meters. Bob can exert a max force of 132 newtons. A minimum torque of 45 Newton meters is required to loosen the bolt. And the question asks, will Bob be able to take off his shoes? All right, so this is what we have here. So we have the ratchet, which is 0.3 meters long. We have his max force is 132 newtons, and we have the minimum torque needed to take his shoe off is 45 Newton meters. So to answer the question of if Bob can take his shoes off, we need to see the max torque that Bob can apply. So to get max torque, we're going to apply the force as far from the center of rotation as possible. So we're going to apply it at the end of the rod, or the ratchet. Also, we need to make sure that the force is perpendicular to the radius, because that's also going to maximize the torque we can produce. So then if we were to calculate this, we get that the max torque that he can apply to the ratchet is 39.6 Newton meters. All right, so no, Bob is too weak, lol. But then Bob remembered the wise words of his father, work smart, not hard. He then realizes that he can accomplish the task by using a longer ratchet. All right, so now this part of the problem is going to ask, how long will the ratchet need to be in order for him to loosen his shoes? All right, so he obviously can't apply more force, so he's going to increase the radius to achieve the same amount of torque. All right, so the minimum torque needed is going to be equal to the minimum radius needed for the ratchet times his max force. All right, so then we're given the minimum torque, which is 45 newtons. We know his max force is 132 newtons, so we can solve for the minimum length of the ratchet needed. So when we plug in those values, we get 0.341 meters. All right. Are there any questions on this? No? All right, sounds good. So we're going to move on to another torque question. Okay, we're not going to look at that. So Bob decides to go fishing. He decides to be efficient, so he rigs his fishing rod such that there is an extra fishing string attached to the rod. 2 fish are on the line, so there are tensions in the string. An alien comes in a UFO and decides to play the claw game to win a prize for his alien girlfriend. The claw grabs the rod as shown below and exerts a force. Basically everything is given, and we want to calculate the net torque about the end of the rod due to these forces. And then we also want to find the direction of the torque vector. All right? So again, this doesn't make sense until you see the problem. So this is what we're looking at here. We have a long fishing rod. This is the regular string, and this is the extra string he attached because he wants to get 2 fish. There's the UFO pulling up on the rod. All right? So we're given all the tension values. So we have T1, T2, and T3. We're given the distance that it's applied to along the rod from the end point. And then we're also given the different angles. But these angles aren't necessarily the angles we're going to use for sine theta, all right? So the main question is to find the net torque. So the net torque is going to be the sum of each individual torque. So there's going to be 3 torques due to these 3 forces. So we're going to sum these torques together. Again, we need to create a positive direction. You can choose either way. I chose clockwise. All right. So now we're going to analyze one torque at a time. Let me zoom in. It's kind of small. All right. So for this one, we're looking at just T1. All right. So T1 is pointed straight downward. Okay. And the radius vector always points from the center of rotation, which is this end, and it points to the application of the force. So it's pointing in this direction. And to find the angle between the two vectors, we need to put the end point of the radius vector at the end point of the force vector. So that's what I did here. I just slid the vector until they reach the same point. All right? We're given this angle above the horizontal as theta 0 right here. And then because this part is pointed straight down, we know that it's making a 90 with the horizontal. So we can find the angle between r and t as theta 0 plus the 90 degrees. All right? So we get 110 degrees for the sine. So again, to calculate torque, the definition is RF sine theta. So if we look at R is the distance from the center of rotation. So we have L over 2. And then we have to multiply by the force, which is T1. And then we multiply by sine of the angle between them. And we just found that the angle is 110. So we have an expression for torque 1 with everything known. All right, so what was it? Okay, so to find R is the distance that the force is applied from the center of rotation. So I'm saying that this is the center of rotation that we care about, all right, because it's fixed to this raft or whatever. And so we need to find the distance that this force is applied to from this point. And that distance is given as L over 2. All right. How I got the angle? All right, so the radius vector points, what am I showing you? The radius vector points from the center of rotation to the applied force, which is T1, right? So our radius vector looks like this, pointed up here. Now to find the angle between the two vectors, we need to slide this vector up further, so it would be like this, all right? And that's what this little diagram is, okay? Now we're given the angle above the horizontal from R, so that's what this angle is, theta 0. And then from geometry, we just know that because this one is pointed straight down, that it has to be making a 90-degree angle with the horizontal. So we have a 90-degree angle here, and then this angle, which was given to us here as 20 degrees. All right? So we get 20 plus 90 gives us 110. All right? What was that? Okay, theta 1. So what you notice is this is like an extraneous quantity, so you don't really need theta 1, but if you wanted to use theta 1, it would actually be a little simpler. You could do 180 minus theta 1, which is the 70 degrees, and you'll get the 110 again, because it's this angle. So you find the same angle, but there's just different ways to find that angle. All right? So moving on to torque 2, we're going to look at the force of tension 2. So this is what this diagram looks like. We have the tension acting at an angle below the horizontal. That's given to us as theta 2. And then we still know that R2, or the angle of the radius above the horizontal, is given as theta 0. So the angle between T and R is going to be the sum of theta 2 and theta 0. So see, we're given theta 2 right here. And then if I extended the radius, it would go up like this, right? And then this angle right here is theta 0. This is so weird. All right? So the angle between them is theta 0 plus theta 2. So when you add those two thetas together, you get 50 degrees. And now we have to do the definition of torque, which is R times F times sine theta. Now we need to look at the R value. So it's being applied all the way at the end of the rod, so it's going to be the whole length of the rod. So it's going to be L. All right? So we have L times tension 2 times sine of the angle we just found, 50. And that's going to be our torque value. All right? Now the last one is the tension due to the UFO. So if we look at this diagram, we have tension acting straight up towards the UFO, and then we still have the radius vector acting up. All right? So we need to find the angle between these two. So if you look at the diagram, it was actually given to us. So the angle between R and T is theta 3. So we can just go ahead and use that value. Now one thing you need to notice is that if we look at torque 3, right? If I were to pull the rod in that fashion, it would cause the rod to rotate counterclockwise, right? So initially I said that clockwise is the positive direction. So if I notice that this is going to give you a negative torque, I need to include that when I do this calculation. So I'm going to throw in the negative sign right there, all right? Because it's going to produce a negative torque. Again, we need to find R. So it's being applied right here. So that's going to be L over 2 plus the L over 4. So that's going to give you 3L over 4. Then again, you multiply by the tension force, which was given. And then we use the angle 70 degrees, which was given. All right. So are there any questions on how we found all those torque values? Are there any questions on the signs of the torque, positive and negative? All right. So going back to the original question, we need to find the net torque, which is the sum of the torques. So we have torque 1 right here, which is positive. We have torque 2, which is also positive. And then we have torque 3, which is negative. All right, so we're going to plug in all those numbers, right? Then when we plug those numbers in, we're going to get negative 617 Newton meters. All right, so because the torque is a negative value, the net torque, that's telling you that the net torque is causing this rod to rotate in the counterclockwise direction, because we said positive is clockwise. So if we ended with a negative value, that means that we're moving the other way. All right. So the last part of this question is to find the direction of the net torque vector. So this is going to be applying the right-hand rule. So the way you do this is you can use the second right-hand rule. So you grab your right hand and you curl your fingers into the direction that the rod is rotating. So again, this negative torque value means that the rod wants to rotate in the counterclockwise direction, okay? So if I curl my fingers in the counterclockwise direction, my thumb is going to point in the direction of the torque. All right, so the torque is pointed out of the page, okay? So is there any question on right-hand rule? All right. Then we shall. So when we deal with torque, we're going to be forced into 3 dimensions. So in the beginning of learning physics, we only deal with 2 dimensions, but once we get to torque, we have to deal in 3 dimensions. So what it's saying is, if I have a vector, say r, and then I have a vector f, right? So if I take the cross product of those 2 vectors, I'm going to get a vector that's perpendicular to both of them, all right? So the only way to be perpendicular to both of those vectors is for it to be in the 3rd dimension. So I couldn't have a vector like this that's perpendicular to both of them. I need to work in the 3rd dimension. So it's either going to be out of the page or into the page.
So whenever it asks the direction, you would say it's out of the page.
Yeah, you would say that. If it asks for the direction, you would say out of the page or into the page. All right? No questions? All right, we'll move to the next one. This one's going to be application of the right-hand rule, because this could show up as a conceptual question, so like multiple choice. So a wheel is rotated by a single force. The wheel rotates such that the torque vector is pointed into the page based on the drawing below. The force is applied to the top of the wheel. In which direction is the force acting? All right, so we have a wheel, right? And we're given the information that the torque vector points into the page. All right, so we're going to kind of be using the right-hand rule, but backwards, because we're given torque and we're given radius, but we don't know the force direction. All right, so if you remember the right-hand rule, you're going to point these 3 fingers, your middle, ring, and pinky. They're going to point in the direction of the torque. All right, So torque is into the page, so I'm going to point them into the page. And then your thumb points in the direction of R, so I'm going to point up because that's the direction of R. And then your index finger is going to point in the direction of the force. Does that make sense? Anybody struggling? All right, so these three fingers, the middle, ring, and pinky, they're going to point into the direction of the torque. And we're given that the torque points into the page. So if that's the page, we're going to point into it, right? Now the radius is always from the center of rotation to the application of the force. So based on that picture, R is pointed upwards, right? So you put your thumb up, and then your index will end up pointing in the direction of the force. Your index. So your index is the direction of the force. All right, so for this problem, the force is going to be directed to the right. All right. You could also apply the second right-hand rule if that's more familiar with you. So to apply the second right-hand rule, you know the torque direction. So grab your thumb, point it into the direction of the torque. All right, so it's into the page, and then your fingers are going to rotate in the direction of rotation. All right, so you know that the wheel has to rotate clockwise. The only way you can get the wheel to rotate clockwise from a force that's acting on top is to apply a force to the right. All right, so you can use either of those two right-hand rules. They both work. Just make sure that you're not using your left hand because you will get the wrong answer every time. Okay? So any questions on the right-hand rule?
The second right-hand rule, so you just do it in the way that, so you do the force, or, so your thumb is the tension, or I'm sorry, your thumb is going to be
The torque. So your thumb is the torque for the second right-hand rule. And then your fingers curl in the direction of the rotation of the object. All right, so whichever one works for you. All right. So we're going to leave torque and we're going to go to angular momentum. All right. So here we have a question. Comets orbit the sun following an elliptical path as shown below. At which point is the comet moving with the fastest speed? All right. So we're going to do a poll and see what everyone thinks. So who thinks point 1 has the fastest speed? What about point 2? Point 3? Point 4? Everyone? Because they're looking at the answers? No, just kidding. All right, so does anyone know why? The radius is larger there? Smaller. Huh? Right, so if we consider this system as a system of angular momentum that's conserved, so we have the equation L equals RmV, right? This is the definition of angular momentum. It's actually R cross P, right? But for analysis, I'm going to take away the cross. L is constant because it's being conserved, right? M is constant because the comet is not changing mass. And then so if we solve for V, because that's where we're interested, the speed, we get V is equal to L over Rm. L and M are constant. The only thing that can change is R, right? So with a smaller R value, we can get a faster speed. And for a bigger R value, we're going to have a slower speed. So looking back at this, the radius from here to here is a lot smaller than the radius from here all the way over here. So that's why the velocity at point 4 is going to be the highest. What is L? L is angular momentum. Any questions on this? No? Right. Considering the fact that angular momentum is conserved. All right. No other questions? All right. We'll move on. The force?
Well, is this in like relation to like the wrench problem?
This is actually not going to deal with that. No, because that has to do with torque, and there's no torque involved in this problem. So the only way that angular momentum can be conserved is if there's no net torque on the system. All right. All right, let's move on. All right, so this is also angular momentum. We have Bob and Bobina are spinning on ice, initially with arms wide open, like Creed. Bob has a moment of inertia of 20.7 kilograms meter squared and is spinning at an angular velocity of 8.1 radians per second. Bobina has a moment of inertia of 22.5 kilogram meter squared and is spinning at a rate of 7.8 radians per second. Bob hugs himself out of loneliness and starts spinning at a rate of 14.1 radians per second. Bobina notices this change in Bob and follows suit. She speeds up to 14.5 radians per second. Which skater has the smaller moment of inertia after retracting their arms? So this is what we're looking at. We got Bob and Bobina. They're going to close their arms and it's going to cause them to spin faster. All right. So this is a basic conservation of angular momentum problem. So we can treat it as if it's a collision, even though nothing's really colliding. So if we look at Bob's angular momentum, we need to set Li equal to Lf. This is the equation for conservation of angular momentum. And if you remember, angular momentum can be calculated as the moment of inertia times omega, which is the angular velocity. So we have I initial, omega initial equals I final, omega final. And we're given 3 of those quantities, so we can solve for the 4th one. So if we do that, we get 11.89 kilogram meter squared. All right, so that's the moment of inertia for Bob after he pulls his arms back. All right. Now we can do the same exact thing with Bobina, and we'll end up with the same exact equation, just different values. And then when we do that, we get a moment of inertia 12.1 kilogram meter squared. So if we're asked to compare the 2 values, Bob's moment of inertia is less than Bobina's. All right. Any questions? No? All right. So we'll move on. So this is another angular momentum question. A rod of mass 50 kilograms and length L is initially at rest and is free to spin about its center. A ball of mass 1 kilogram moves at a velocity of 20 meters per second as shown below. It hits the rod halfway between the center and the top of the rod. The ball sticks onto the rod and rotates at an angular velocity of 5 radians per second. The moment of inertia for the rod is calculated as 1/12 ml squared, and the moment of inertia for the ball is mr squared. So it's treated as a point mass. All right, and the question asks to find the length of the rod. Okay, so to start off, we need to recognize that this is going to be a problem dealing with conservation of angular momentum. So when it comes to collisions, that's usually what you're going to deal with is angular momentum conservation. So we have delta L equals 0, which is the same as Li equals Lf. Oh, I should have erased that. You don't need to know that. All right. So this is what's happening. We have a rod that's vertical, and then a ball is going to hit it halfway between the center and the top, and then it's going to stick to it and cause it to rotate at a constant angular velocity. Okay? Assume everything frictionless to make lives easier. Now all we have to do is set Li equal to Lf and then analyze what Li is and what Lf is. So initially we have nothing rotating. The only thing that's moving is this ball, but it's moving in a linear fashion. But we can always have angular momentum about a point. So the definition of angular momentum is r cross p, where p is the linear momentum. All right, so we have r cross p here. That can be simplified to rp sine theta. And if we look at a diagram over here, if you do r sine theta, r sine theta is going to be L over 4, no matter where the ball is on its path. All right, it's a constant. So we can replace the whole r sine theta by L over 4. And then P can be calculated as mass times velocity. All right. Now looking at the other side, because we're dealing with rotation, we can do the easier formula, which is I omega. All right. So now to calculate I, we need to take into consideration the two different I values that we're going to have, because we're going to have an I value related to the rod, and we're going to have an I value related to the ball that's stuck to the rod. All right. So we know the rod is calculated as 1/12 ml squared. We're given the mass, and we're not given the length. That's what we're looking for. And then for the ball, we're going to use mr squared. So r is going to be the distance from the center of rotation to where the ball hits. So the ball is going to get stuck right here. That's a distance L over 4. So that's going to be our radius for our I calculation. So we have mr squared here, where r is L over 4. We square that, and then we multiply this whole I by omega. All right? So then from here, everything is just algebra. You want to solve for L. So you get L is equal to 1/4 mv divided by 1/12 m plus 1/16 m omega. All right? And then all the values are given to you. Plug in those values, and then you end up with 0.236 meters for the length of the rod. So does anyone have questions on that? Okay. All right, so this is, I think we have 2 more angular momentum problems. A can of Vienna sausages is rotating at a rate of 10 radians per second on a frictionless surface. 2 identical cans of Vienna sausages with no spin are dropped on top of the spinning can. They eventually all spin together. What is the final angular velocity of the cans? So again, the way you kind of figure out if it's going to be an angular momentum problem is if you see rotation and then you see moments of inertia, as well as a collision. For the ice skating one, there wasn't really a collision, but you could see that the moments of inertia were changing, which is going to change your angular velocity. But this one is clear to see that there's a collision occurring, and so there's going to be conservation of angular momentum. All right. So again, we do Li equals Lf. And then we have the simple equations, I initial, omega initial equals I final, omega final. And then we have this relationship for I final and I initial, because I initially is just the one can spinning. But the I final is going to be all 3 of the cans spinning. So all you have to do is add the moments of inertia 3 times. So you have 3 times the original moment of inertia for the final moment of inertia. You throw that into your equation, and you notice that the i's cancel out, and that you can find omega f as 1/3 of omega initial. You have a question? Okay, so the way you know that there's conservation of angular momentum is based on Newton's second law, which is the net torque is equal to dl dt. So this is the change in angular momentum. So if you want angular momentum to be conserved, what's true is that the net torque has to be 0 on the system. So if we look at the system, is there any torque acting on it? No, because there's no friction, so it's free to spin. And so the only force that's applied is when the 2 masses hit each other. The friction is going to cause them to eventually spin together. But that friction is an internal force, so it's not going to contribute to this net torque. So you're going to get conservation of angular momentum in these problems. Also, I don't think he would give you a problem that had to do with a net torque affecting angular momentum, because that's a little too complicated. So are there any questions on this problem? All right. So we have our last angular momentum problem. A tortilla is spinning at a rate of 1 radian per second on a frictionless surface. Bob drops his arepa onto the tortilla. The arepa is spinning at a rate of 5 radians per second, but in the opposite direction of the spinning tortilla. They eventually start spinning together. We're given the mass and radius of both food items, and we're given that the moment of inertia for a disk is 1/2 mr squared. And we need to find the final angular velocity when they're spinning together. All right? So this is going to be very similar to the other one, except for the fact that now the I values are going to be different. And also, if you notice, we have rotation in both directions. All right? So what we need to do is define a positive direction. So I defined it as this direction. So omega 1 is in a positive direction, and omega 2 would be in a negative direction. All right? Let me erase this because this is confusing. All right? So I'm going to assume that omega f is going to be in this direction. All right? So again, we do conservation of angular momentum. So we have Li equals Lf. But now, what's different is we have two different angular momentums in the beginning. So we have an angular momentum from the tortilla, which is going to be positive because it's rotating in the direction that I said is positive. And then we have the angular momentum of the arepa, which is negative because it's rotating in the opposite direction. All right? And then, when we're analyzing the final angular momentum, we do the same thing where we add the moments of inertia together because they're going to be spinning at the same rate. They're basically going to be stuck together. All right? So then we can solve for omega f. That's what we're interested in. And then from here, we substitute I for 1/2 mr squared. Now we have to make sure that we plug in the right m's and the right r's for each I value. So the two are different shapes, different dimensions. So we need to make sure we put the right dimensions in there. All right. And then we throw in all the numbers. Then we get a final value. So we get omega final is going to be negative 2.176 radians per second. Now, what does that negative sign mean?
It's the opposite side that you chose.
All right. So the negative sign means that it's moving in the opposite direction that I chose. So I chose omega f to be this way. So if I get a negative value, it actually means it's going the other way. All right? Are there any questions? No? All right. So now we're going to get to our last topic, which is oscillation. Actually, there's another topic afterwards, but we have oscillations. We're going to have two problems. First one is a pendulum. This one's pretty straightforward. We have a pendulum with a mass of 5,000 kilograms. The pendulum is on the surface of the Earth. The period of this pendulum is 2 seconds, and we have 3 questions to answer. We need to find the frequency, we need to find the angular frequency, and we need to find the length of the pendulum. All right? So to find the frequency, we just use the definition of frequency. So the definition of frequency is 1 over period. So the frequency can be calculated as 1 over the period, which is 1 over 2 seconds, so we get 0.5 hertz. All right? And the way you interpret frequency is cycles per second. So if you have a frequency of 0.5 hertz, that means it's doing 0.5 cycles in 1 second. Make sense? All right? So the next question asks to find angular frequency. So this is actually just a conversion from frequency to angular frequency, which is omega equals 2 pi f. So we just found f, so we can just plug that in, and we get pi radians per second as omega. All right? And omega is very different from frequency because this is angular frequency. So it has to do with how many radians per second rather than how many full cycles per second. All right? And then the last question is to find the length of the pendulum. So to do that, we need to use the formula from our formula sheets for a pendulum, which is omega equals the square root of g over L, right? So we know g because it's a constant and we're on Earth. And then omega we just found as pi radians per second. So we can solve for L. We get 9.81 divided by pi squared. And the final length is going to be 0.994 meters. All right. What do you guys notice about what was not used in this problem? Right. So the mass wasn't used at all in this problem. And that is because the mass at the end of the pendulum doesn't affect at all its oscillating properties. So whether you have a feather down here or a cannonball, you're going to have the same frequency, the same period. All of that will be the same. All right. So any questions on this problem? What was the answer? It's 0.994 meters. Also, you can find this review online at that website. All right. No questions on pendulums at all? All right. So this is our second oscillating system. We have a spring. It's attached to a mass on a horizontal frictionless surface. The mass is pulled a distance and released. At a time of 2 seconds after being released, the mass is located 3 meters from the equilibrium position. The angular frequency is pi over 6 radians per second. The mass is 100 kilograms. And then we're asked to find the amplitude of oscillation, the spring constant, the maximum potential energy, the maximum kinetic energy, and then also if at a random time the kinetic energy is 293.48 joules, what is the potential energy at that instant? All right. So we're going to look at this. So this is what the problem looks like. This is the mass and the spring at equilibrium. And what I'm going to do is I'm going to pull it over to a distance, and then I'm going to let go of it, and it's going to start oscillating. All right. Now the problem gives us that when I pull it over here and I let go of it, after 2 seconds of letting go, it's going to be located a distance of 3 meters from the equilibrium position. All right. So the first question is to find the amplitude. So does anyone have an idea of how you would find the amplitude? Right, so we're going to use our equations of motion, which are given to you in the formula sheet. Actually, this is the only equation of motion that's given to you, this position one. So we have x of t is equal to a cosine omega t, all right? Where a is the amplitude, and the way this equation is used is if I plug in a time for t, I can figure out the position of the mass at any time, all right? So this problem is working backwards because I'm looking for amplitude, and I'm actually given a distance and a time. So at time equals 2 seconds, I know I'm at 3 meters, and I can plug in 2 seconds here, and we were given omega as pi over 6 radians per second. All right? So when you plug in all those values, you get 3 over 0.5, so you get 6 meters as the amplitude of oscillation. All right? So the second question asks to find the spring constant. So what do you think you would use to find the spring constant? So if you look at your formula sheet for oscillations, you don't have many equations. So it's pretty easy to figure out which one to use, the only one that has k in it, right? So omega is equal to k over m. We were given the mass, we were given omega, so we can find k as omega squared m. So we plug in those values and we get k as 27.416 newtons per meter. All right? So now the next two problems are going to be associating energy with oscillations. So the first problem is to find the max potential energy. And so to do that, we need to figure out what potential energy is going to be in the system. So we're not going to have gravitational potential energy, but we're going to have spring potential energy, right? So if you remember, spring potential energy is calculated as 1/2 kx squared, which is right there, 1/2 kx squared. And if we want the max potential energy, we need to maximize all the components of this formula. We can't maximize 1/2 because that's just a number. We can't maximize k because that's a constant. But we can maximize x because it's changing position all the time, right? So we need to put the max displacement from equilibrium. So that's just going to come out to 1/2 ka squared because a is the maximum displacement from equilibrium. We plug in all the values because we found k, we found a, and we get 493.48 joules for the potential energy. All right. So the next question is to find the max kinetic energy. So kinetic energy is just 1/2 mv squared. But if we want the max kinetic energy, we need the max velocity. All right? And to find the max velocity, you can look at the equation of motion for velocity, which, since it's not on your formula sheet, the only way you could figure it out is to take the derivative with respect to time of this equation, and that'll give you this velocity equation. All right? So now if we want the maximum velocity, we need to maximize all the components of this equation. So a is a constant, can't change it. Omega is also a constant, but sine omega t is always changing. And the way sine omega t works is that it oscillates from -1 to 1 and never goes past it. So the highest value that sine can be is 1. Therefore, the maximum velocity is just a omega. All right? So our maximum velocity turns out to be pi meters per second. And then we plug that into our 1/2 mv squared, and then we get 493.48 joules, which happens to be the same as our maximum potential energy because conservation of energy, all right? So because there's no friction in the system, we're going to have maximum potential energy here with a 0 kinetic energy because it's at rest. And then when it passes through the equilibrium, we're going to have a maximum kinetic energy, and we're going to have a 0 potential energy because the spring is not compressed nor stretched. All right, so all that's happening is all of the potential energy is being converted into kinetic energy. Now for the final problem, it asks us to find the potential energy when the kinetic energy is 293.48 joules. So what we need to realize is that the total mechanical energy in the system is equal to the maximum kinetic energy and also the maximum potential energy. All right? So this is the most energy the system has. It's actually the energy that the system has at all times throughout the oscillation. All right? But as it's oscillating, what's happening is k is changing and u is changing, and they balance each other out. So if one goes down, the other one goes up. If one goes up, the other one goes down. All right? So then we can actually just plug in our values. We know E has to be the k max, which is 493.48, and we're given that at a random time, k is to be 293.48. So we can find the potential energy at that instant, and we get 200 joules. Oops. All right. Any questions on oscillations? What was that? F over D? I don't know about that equation. I've never heard of that ever. So I don't know what to tell you. All right. So no other questions on oscillations at all? All right, so we have two more problems. These problems have to do with static equilibrium. All right, so this is going to deal with torque and Newton's laws. Okay, so this is the problem we have. We have a beam that's resting on this pivot point right here. So this is the center of the beam. And then we have mass 1 on the left side at L over 3 distance from the center. We have M2 all the way at the other edge of the beam. And then there's going to be an M3 placed on this beam such that this beam will be balanced. So the goal is to have this beam perfectly still without touching this pivot point. All right? So another way to interpret that is that the normal force exerted by this pivot point is supposed to be 0. All right? So when it comes to static equilibrium, if you look at your formula sheet, you're only going to see two things, and it's basically the definition of static equilibrium. So to achieve static equilibrium, both of these conditions must be met. All right? So we need the net force to equal 0, and we need the net torque to equal 0. So if you have a question on static equilibrium, the first thing you want to do is just go to these equations and figure out what to plug in. All right, so we're going to start with force. So we need to look at all the forces. I'm going to say that the positive direction is up. All right? So if you look, we actually have 6 forces. We have the weight of this mass acting on the beam. We have the weight of this mass acting on the beam and this mass. We also have the weight of the beam, which is acting downward from the center point. All right? We have 2 normal forces, N sub O and N sub P, from the 2 pivot points. And those are all our forces. So the only ones that act upward are the normal forces. So we have NO plus NP. And then all of the other ones are acting downward because of gravity. So we have minus MBG, minus M1G, minus M2G, minus M3G. All right? MB is the mass of the beam, and then these are the 3 different masses. All right? So the question we're actually asked to find is, we want to find the delta X value needed for M3 to achieve a 0 normal force here. So depending on where we put this M3 is going to change the normal force at this pivot point. All right? So we need to find that delta X. So if you look at the force equation, it actually doesn't have anything to do with distance, right? So it doesn't actually help you at all in this problem. So now we go to the torque equation. So net torque has to equal 0. And the best thing to do is usually to focus on the center of rotation. So if you can imagine that this beam is going to rotate about this pivot point, we're going to use this as the center of rotation. All right? So now when we calculate all the torques, it needs to be in reference to this position. So again, I'm going to define a positive direction. I'm going to make counterclockwise positive, and this is just saying that we're starting at this position. So we're finding the torque around this position. All right? So now we're going to have a torque due to the forces. So if we look at M1, the force of M1 is acting downward, right? So we have M1G down, and this force is actually going to cause the beam to rotate in a counterclockwise direction. All right? And I already said that's going to be a positive direction, so I'm going to put that as a positive torque. So I have M1G as the force, and then we need the radius, which is going to be the distance from center of rotation, which is L over 3. All right? So that's where I get this first term. And now if we look at the forces at the center of rotation, we have 2 forces. We have N sub O, which is the normal force acting on the beam, and we also have the weight of the beam acting right there. But what we notice is that these 2 forces aren't going to attribute any torque to our problem because they're at a distance 0 from the center of rotation. So these 2 forces don't apply any torque. So now we're left with 3 more forces, but the condition we set is that NP is going to be 0, so we don't have to deal with NP at all. So now we have the weight of M3 and we have the weight of M2. So we're going to start with M2 because we know the distance. So if we look at just M2, it's going to cause the beam to rotate in the clockwise direction. And clockwise is actually the negative direction from what I said. So I'm going to put a negative value for the torque. So I'm going to have M2G times its distance from the center, which is L over 2. And now if we look at M3, it's going to be similar, but now instead of L over 2, it's going to be delta X because we don't know the distance that it is. All right? So now we have an equation that has delta X, which is what we're looking for. We're given L, we're given M, all the M's, and we know G. So we can solve for delta X. We get this equation, and when we plug in all our values, we end up getting that X, or delta X, is 2.5 meters. All right? So if we look at our drawing, L, the total length L is 5 meters, right? And I'm saying that delta x is 2.5 meters. So what that means is that M3 would have to be placed directly on top of M2 in order for this system to be in static equilibrium and not have any normal force at this point. All right? Does that make sense? All right. What do you want to see? All right. So now the next thing I want to show you is how to choose where to rotate. So it's not always clear to see where you should pick as the center of rotation, but I want to let you know that it doesn't matter where you pick. So I'm going to do an example of picking M1 as the center of rotation. All right? I'm going to show you that it doesn't matter. So we're going to do the net torque again, but this time we're dealing with the center of rotation at M1. All right? So now we're going to have a lot more terms here. So we notice that M1 is not going to contribute any torque because it's acting at our center of rotation. We have NO that's going to contribute torque. We have MB that's going to contribute torque. We have the two masses, and that's it. All right? So if we look at the first term, we have the normal force multiplied by L over 3. So looking back at the drawing, this is our center. Normal force is causing it to rotate in the counterclockwise direction, which is our positive direction. So I'm going to make it a positive torque. So I'm going to take this force and multiply it by its distance, which is L over 3. All right, so that's how I got the first term. Now for the second, for all these other terms, it's just the masses, and they're all going to be negative because they're all going to cause a clockwise rotation. All right, so the mass of the beam is acting at the center of the beam, which is also L over 3. So that's where I get the second term, MBG, L over 3. Now for M3, it's also going to be downward, so that's going to be negative. We're going to have M3G, and the distance from M1 is going to be L over 3 plus the delta x. All right? So that's where this term comes from, L over 3 plus delta x. And then the final term has to do with this second mass, which is at a distance of L over 3 plus L over 2. All right? So that's where we get this term. So as you can see, this is a much bigger equation with a lot of variables and whatnot. So it's not desirable to go this route, but you can always get the right answer. So I'm going to show you how that comes about. We don't know NO, right? But we made a force statement in the beginning that has NO in it. We didn't use it initially because we didn't need it, but now we're going to need it. So NO is going to be the sum of the weights. All right? So we have NO equals all of the weights added together. Now we have to plug that into our already long equation, and it becomes even longer. So we have this huge equation right here, and then the beauty of it is when you distribute everything, a whole bunch of things start canceling out, right? And then you get to the final equation, and it turns out to be the exact same equation that we did in the first one. So pretty nifty stuff. So yeah, that's just to show you not to be worried about where you choose the center of rotation, because you'll still get the same answer. Just some ways are easier. So typically pick the center of rotation that you think is going to rotate about. All right, any questions on this type of static equilibrium? All right. You good? All right. So we're going to do one more static equilibrium problem. So this one involves pulleys. All right. So we're given two pulleys right here, one with a big R and one with a small r. And we know the relationship between the r's is the small r is 1/5 of the big R. We're given the second mass. We're given this angle of incline. This is also frictionless. All right. And the problem is going to ask to find the mass of M1 so that everything is in equilibrium. So basically, we want nothing to move in the system. So again, we're going to do our net force equals 0 and our net torque equals 0. So just Newton's second laws, but changing the acceleration to 0. All right. So now what we need to do, will it say something about static equilibrium? It will have to say something like no acceleration or that it's in equilibrium. So if you get a word problem like this, it will tell you that it's in equilibrium. And also, if you didn't know it was in equilibrium, you could still do F equals ma and net torque equals I alpha. And then as you're doing this, you're going to realize that A is 0 and alpha is 0. So then you get back to the same equations. All right? So the way we do this is similar to the other pulley one that we did. So we need to do the force diagrams on each mass, and then we need to do a torque diagram on the pulley system. So I'm going to start with the pulley system. So we have a tension 1 pulling it from mass 1, right? And this is acting at the smaller pulley. So it's acting at a radius small r. And then we have a tension 2 that's suspended over the edge. And that's going to be tension 2, and it's attached to the larger radius pulley. All right. So now we need to find values for T1 and T2 so that we can plug them into our torque equation. So to do that, we always have to do our free body diagram on the other masses. So if we look at the first mass, the only forces acting on it are the normal force and gravity. Oh, and the tension force, of course. So we have tension 1 acting upwards. And the only thing that's balancing this tension 1 is this component of the gravity that's acting down the incline. So this component is actually m1g sine theta. All right. So we get that T1 is equal to, well, I'm going to call this T0. T0 is equal to m1g sine theta. All right. So then we look at this part of the pulley, right? So we have two strings here and one string here. So we have one tension this way, and then we have two tensions this way, as shown here. And it turns out that these two tensions have to be equal to each other because they're in equilibrium. So nothing's moving, so the strings have to have the same tension. So this T0 is actually the same as this tension in this part of the pulley. All right? And then the T1 has to balance out this force. So we have T1 plus T1 minus m1g sine theta has to equal 0. So that's just another free body diagram. All right? And now we solve for T1, and we'll get that T1 is equal to m1g sine theta over 2 because of the two tensions. All right. Now we do the free body diagram on the second mass, but that one's much simpler because it's just the tension and the weight. So for it to be in equilibrium, the tension has to be equal to the weight. So that's where we get tension 2. Now the rest is doing the net torque about the center of rotation. So we're going to use our net torque, set it equal to 0. And again, we need to choose a positive and negative direction. So in this problem, I made counterclockwise positive. So if I look at T1, it's going to cause the pulley to rotate counterclockwise. So that's going to give us a positive torque. And then T2 is going to cause the pulley to rotate clockwise, which is a negative torque. So we get T1 small r minus T2 big R. all right? And we need to set that equal to 0. But we don't know T1 or T2, so we're going to throw in these equations that we just found. We're going to put them in there. So put them in there. We just do algebra. We notice that the G's cancel out and the R's cancel out. And then our final equation is M1 is equal to 10 M2 divided by sine of the angle. All right? So then when you plug in all your values, you get 2,000 kilograms for mass 1. So this is the mass that's needed in order to keep everything in equilibrium. So to make sure that none of the system is moving. All right? Any questions on equilibrium? Yeah, so R wasn't given, right? But what we notice here is that the R's cancel out. So it doesn't matter what R is. All right. Any questions? No? All right. So I do want to go over one thing about oscillations that might show up on the test, but I didn't make any problems for. So he did mention about an oscillating system with damping. So damping is just having a fluid or friction causing the mass to slow down over time. So an example like this. And if you look at your formula sheet, he gives you the equation of motion for it. And then he also gives you this value, which is omega d, which would be the frequency of oscillation for a case like this. That omega d is related to k, which is the spring constant, m, the mass, and then b, which is the damping coefficient. The damping coefficient has to do with whatever liquid it's in, all right? So I just want to tell you that he probably won't have something as complicated as the oscillation problems we had just done with a damping one. So if there is a damping one, it's probably just going to be using these two equations, all right? And understanding what damping means. So if a system wasn't damped, it would oscillate forever, indefinitely. But if it is damped, it's going to slowly die out like this, all right? So that's the definition of damping. All right. Another thing to note is that we did have a section on modulus, but your main FRQ questions are going to come from torque, angular momentum, and oscillations. So modulus probably won't show up for a free response. If it does show up at all, it's going to be a multiple choice. And he gives you all 3 equations for modulus. I don't remember them, but it'll be on the formula sheet, and it'll probably be a conceptual question if it shows up at all. All right?
What is modulus?
Modulus, it has to do with the elasticity of a material. So there are 3 different modulus that you learned. So there's I don't know the names, but one has to do with stretching something. One has to do with I'll just draw it. So the stretching one, if you apply a force to like a rod, you can cause it to stretch, right? Similar to like a rubber band. You pull it, it's going to stretch. The other one is something like this. So if you originally had just a rectangular prism and you applied a force at the top and caused it to slide a little, that's another modulus that he gave you in your formula sheet. And then the last one is just volume expansion. So something that just changes volume due to force. And all those equations are given to you. All right? And then just some other study tips and test taking tips. Big thing, make sure that when you're doing the problems that you convert all your units to SI units, because if not, you're going to get the wrong answer. And then also just try to understand all the formulas in your formula sheet, including all the variables associated with the formulas. And then my favorite tip is when you're doing the test and you feel stuck, to just look at your formula sheet and just look at all the different equations. Also, when you see a question, write down all the known values that you have like I've been doing with these problems where I list all the knowns at the very top. That way you know what you're working with and what equations you could use, maybe. All right? All right. So does anyone have any questions about the test? Nothing? All right, well, that's all I got for you. Oh. The last two problems that I just showed you for static equilibrium, I actually just made them, so they're not in the review yet, but I'll put them up tonight. All right. You're welcome. Yeah. Hold up. 17.
What was the answer to the last one you did? This
35. Oh, it was 2,000 kilograms. You got a question? Huh? No, I was just counting people.
What are the chances that you would put static in?
The chances. I'm not too sure.
When he was mentioning in class, it didn't seem like it was
Yeah. The chances of him probably aren't likely, but if they do show up, it's actually easier than if there's acceleration, because you're setting everything to 0, so it's a little easier.
Thank you. Get my phone.
But if you know how to do the one with the mass on the incline with friction, if you can do that one, you can do static equilibrium easy.
So, alright, I don't have the barcode,
Oh, okay.
but I have this other guy, and he had this problem on the test. Do you know how to do it?
What are you supposed to find?
I
Find
looked at
I?
it on the test, and I was like, oh.
You need to find I?
What's up? How you doing?
Yeah, so that's what you need to do. You need to do the integral.
Thank you.
I'm sorry.
What are you sorry for?
I don't know. I just said.
It's all good.